Building an AI model that detects tumor in chest scans from scratch will require millions of labeled medical images, months of compute time, and a budget that most hospitals do not have. Yet, many production medical AI systems are deployed often without any of these three things. Well, the secret is transfer learning, and in this video, I'm going to break down everything you need to know about transfer learning. Hello guys, welcome to Tech with Prince James. In this channel, I explain AI concept through storytelling.
Let's look at the main hurdle today. The problem with training models from scratch.
When you train a model from scratch, every pattern that it needs to recognize has to be learned from the dataset. So for a tumor detection model, that means the model has to learn what an edge looks like, what a texture looks like, what spatial contrast looks like, all from medical images alone. That's a problem for two reasons. First, annotated medical imaging datasets are expensive to build. Every scan needs to be labeled by a qualified radiologist. Second, the model needs enough labeled images to learn reliably. And in medicine, that volume is rarely available, especially for rare conditions. Transfer learning solves these two problems. But to understand how, you first need to understand what happens inside a model when it learns anything at all. When a deep learning model trains on images, it doesn't learn everything in one shot. It builds understanding in layers. Literally, the early layers of a neural network learn low-level features, edge, curves, color gradients, and basic shapes. The middle layer combines those low-level features into higher-level patterns. So you have textures, structures, objects, paths. The final layer then learns task-specific features. It learns that distinction that it's able to tell the difference between a cat and a dog. This layered structure is the key insight behind transfer learning. A model trained on photographs of everyday objects learns the same foundational visual skill it would require to read a chest scan. The only thing that needs to change is what the final layer of the neural network learns. This is where pre-training comes in. A model like ResNet is trained on ImageNet dataset, which is basically a dataset of millions of labeled images. Through that training process, the model develops a deep generalized understanding of visual structure. By the end of that pre-training, the model has no idea what a tumor is, but it knows how to process visual information at every level of complexity. That knowledge is stored in the model's weights, which are numerical values across millions of parameters that encodes everything the model has learned. Those weights are what gets transferred in transfer learning. So let's take for instance that a hospital takes that pre-trained ResNet model and wants to adapt it for tumor detection. This is called fine-tuning, and here's exactly how it works. First, the hospital team would need to replace the final layer of the neural network with a new output layer designed for a medical task. So instead of outputting cat or dog, this new layer would output tumor present or no tumor detected. Then the hospital team would need to make decisions about the rest of the neural network, like which layers need to be frozen and which layers needs to be updated. Freezing a layer of a neural network basically means the weight will stay fixed during training. So basically, that frozen layer keeps everything it learned during pre-training. Typically, the early and the middle layer are what gets frozen because their knowledge of edge, texture, shapes is already useful and doesn't need to be changed for the new tasks. But the layers that are closer to the output get unfrozen. These are the layers that will be retrained on a medical imaging dataset because they need to develop task-specific understanding, like learning what distinguishes a malignant mass from a benign model in a chest scan. The result is a model that combines the broad visual foundation it's amassed from millions of data sets with targeted medical knowledge built on a fraction of that data. So the pre-training process took millions of data sets, but this fine-tuning phase only requires thousands of medical imaging data sets. The benefit here is that the hospital spends less, and also it trains the model faster than what it would require to train it with millions of images. Now, transfer learning is not just about medicine. That's just one example. It is a standard approach that many production AI systems are using today. The sentiment analysis tool that your favorite brand uses to read customer reviews has been fine-tuned on a pre-trained natural language processing model. That object detection system in your phone's camera has been fine-tuned using a model pre-trained on millions of images. So in every of these cases, the same logic applies. Pre-trained on a large dataset to build foundational knowledge, then fine-tuned on a smaller task-specific dataset to develop targeted capability. So the pre-training does the heavy lifting, while the fine-tuning does the specialization. This is why open source models like BRT, ResNet, and Llama have become so valuable, because they give teams a trained foundation to work with without the compute cost of starting from scratch. Transfer learning works because intelligence is layered. So basically, the skill a model builds solving one problem can be transferred to new problems. With transfer learning, you don't have to train a new model from scratch every single time. You can just build on an existing one. If you found this explanation helpful, make sure to hit that subscribe button and stay close to this channel, because over here, I break down AI concepts in a way that makes sense. Bye, and see you in my next video.